Thank you, Mark, and thank you all for coming. I want to talk a little bit about Python and what you can do with Python on Flink. And like Mark said, you will learn about the use case after that too. But before we start, I'm curious how many of you are either currently using Python or would like to use Python for data processing at large. That's a good group. And how many of you are working with Flink or might work with Flink in the future? Okay, so there are a lot of people that want to use Python and there are some that want to use Flink. Let's think about how we can bring the two things together because they don't go along traditionally. Python, data science, background machine learning space, very rich ecosystem, Flink, JVM-based runner, typically only approachable for Java folks. And there's this disconnect. So the agenda is why do we look at this at Lyft? Why do we consider Beam? Then what is it in Beam that enables to run something like Python on Flink? Some details about the runner, how this works internally with Flink, and then also next steps in this area. So Lyft is a ride-sharing company and brings together, matches passengers and drivers. To do that successfully, a lot of decisions need to be made in real time. Demand and supply need to be balanced. You, as the user, expect to have the latest information, the location of the car. You want accurate pricing. You want to know when things change due to traffic conditions. So you can imagine that there's a lot of decision-making and processing that needs to happen fast to provide a good experience to the users and to the drivers. I'm a member of the streaming team at Lyft. We have a streaming platform that several other teams are using as part of a larger data platform. So this is just a streaming platform, and Flink is the framework of choice that we use for streaming. Data is typically delivered through either Kinesis and slowly moving towards Kafka. And then it is results are given to destinations for downstream consumption. There's an entire infrastructure downstream with batch processing and other tasks, and of course serving systems. But what we want to look at is the streaming part. How do we write applications with Flink? As I said, traditionally it's a Java programmer's job, writing with the Java API a job that runs on Flink. And that works fairly well. All the frameworks in this space, and Flink is no exception, are becoming more approachable with the support of SQL for streaming, which actually covers a good chunk of use cases that are like simple jobs with filtering, aggregations, and so on, that don't require a lot of programming. In fact, they can be expressed in a declarative way. But there is this space that is neither Java nor SQL, which is machine learning related. And as I saw, the rising interest in Python to do programming with Python using all the libraries that are out there in the Python ecosystem to do data processing and more sophisticated things. So we would like to use Python, and actually Lyft has a lot of Python code and a lot of Python developers. They can't use streaming because there's no support in Flink to use Python, to write a Flink pipeline with Python. So that's where we started from. Where we want to get to is we want to solve this, right? So we want to overcome some of these challenges. The generally big data ecosystem is Java, JVM based. We have different use cases. We want to support different language environment, and Python is particularly for the machine learning space of relevance and interest. And generally, it's also nice, this plays into what Beam solves, to have a unified way of a unified model to think about data processing, as well as a unified API that can actually be used to write things that doesn't change dramatically between different environments, and that also doesn't bear the cost of switching engines and operationalizing them, because that's a significant effort. So the Beam vision is just that, right? You have different languages, SDK in different languages, and you can run them on different execution engines. As a user, you know a Beam model, you write it with your language of choice, you write your pipeline, and then you can pick an execution engine to execute it. So far, so good. Multi-language support in Beam. Beam started with Java, like Tyler said. You can write a pipeline in Java, you can run it on a Java-based runner, at least the open source runners. That's how it started originally. In 2016, efforts started to enable cross-language support on language portability. The first other SDK was the Python SDK that appeared in 2017, and that would only work on data flow. And in 2018, the Go SDK was added. The Go SDK was the first SDK to work on the portability framework, i.e. on the framework that enables any language to run on any runner, the ultimate goal of Beam. And in end of last year, and the Flink, the Python support on Flink became a reality through Beam. And next is to have cross-language pipelines and to have more runners to support all of this. I'm going to skip over this because you already saw a Python snippet, but this is a typical pipeline. We read data from somewhere, we process the data with windowing, with different result emit options, and then write it eventually somewhere else. So nothing particularly interesting. What is the nice thing about Beam is that this would look similar in every language that it supports. And like I said, it would run on many different engines without change. So Beam portability, these slides, they look familiar, and we take portability serious, right? Even the slides are portable. Originally, we have the Java-based runners on the right side, and all the open source projects, all Java-based runners, and they understand pipelines that were written in Java and are a Java representation. Well, that's a problem once you start to add the first SDK that's not Java-based and Python, right? So Python would only work on data flows with special case translation, nowhere else. So that's not what we want. What we want is that we use different languages. We have a pipeline representation that is language agnostic, and then we can run those on runners that understand, that can process that pipeline and delegate it in a way so that the language-specific things are executed in a native environment. So right now, it's Dataflow, Flink, and lately Samza, who add that support. And we hope that other runners will move towards the portable model. It's a pipeline representation that is not Java. It's done in a way with protobuf that any other language can generate it too. And the first language that did that immediately from the starting point was Go. Go only works with portable runners. So now let's look how this works in the context of the Flink Runner, because that's really what we are here at Lyft are interested in. You have the pipeline written in Python, and the user would submit it using Python, a Python command. And the interesting piece in that is a job endpoint. That's the address of a runner that can receive the pipeline that the client, the SDK client, has created. This runner is a Flink Runner in this case. It takes that pipeline and it translates it into a Flink job graph using Flink's native API, which is data set or data stream, depending on whether it's batch or streaming. And from then on, it's like any other Flink job. It's being submitted to the Flink cluster. What's special here is that the operators inside the graph are beam operators supplied by the Flink Runner. They understand how to coordinate work at execution time between Python process and the Flink tasks that run in the Flink Task Manager. So those SDK workers, they are Python processes. They can contain all the dependencies that you would want to use. And there is a protocol and an API, FN API, that controls how code can be executed inside SDK harness using the Flink Runner. So there are different planes that control separate aspects of that API. Control plane is the top level interaction, really, that where the runner tells the SDK what functions will be needed, because functions need to be deserialized in some way and prepared before they can execute. And then bundling is a grouping of many records. And the data plane is the interface that via streaming gRPC transfers the actual records between runner and SDK worker. And then there's also state and logging. So all the things, the execution is orchestrated by the Flink Runner, but the actual work happens in an SDK worker, which is a Python process. We don't need to go into all of the details, but here's one example for FN API, the bundle processing, which is the most important part of the execution. So the Python functions are registered with the worker. That's a little more expensive operation because they need to be deserialized and ready when the bundle processing starts. And then you have the large boundary with the bundle boundary, begin and end bundle. Could be a little bit more expensive operations, which some setup and teardown overhead is involved. And in between, we have hopefully many elements that can be processed fast. So this is not a batching. This is just a grouping that still benefits from pipelined execution. The one aspect of the data plane is that it should be of interest is where does data get serialized and deserialized. In Beam terms, those are called coders, coding and decoding, encoding and decoding. This happens on the SDK side, so this would be Python code. The Flink Runner does not need to understand what the data is. Those are just opaque binaries that are being passed back and forth. The only exception of that is it needs to understand keys so that it can do shuffles and group by key, and it needs to understand windows, which are wrappers in the data tuple. So yeah, people can write their custom encoding, specialized things in Python in this case, and they would execute inside the workers. So the Flink Runner, what is it doing, or what is the runner doing in general in this entire portability picture? It provides the job service endpoint, it translates the pipeline into the native whatever the engine provides API, and Flink will be different between Flink and all the other runners. It provides the gRPC endpoints to drive the execution. It manages the processes, the SDK processes, so they need to be brought up and started and managed, and drives the bundle execution, and then manages state. That's important for stateful processing and streaming. The runner manages the state. The runner provides the fault tolerance. The runner is orchestrating the entire processing. The worker is really like a disposable process. It could go away at any point in time, and we could bring up a new copy, and it would resume processing. And this code is not Flink specific. Most of the code is common, so that other runners, other Java-based runners will benefit from that as well. And the Flink specific things are really how we package the job server, which dependencies go in there, how does the translation work from a portable pipeline to Flink, and then how is state handled, how is the job launched. At Lyft, we have done a couple of customizations. First of all, we need streaming sources. Today, no streaming sources are available in the Python SDK. In general, the connector situation looks a little bit unfriendly still on the Python side. The solution that we really have for that is to have cross-language support, because Java has a large library of connectors. They are more mature. We would like to use them. We would like to be able to use them with Python. Not there yet. What we have done here at Lyft is to use the Flink connectors that we already use in other pipelines in Java Flink jobs, and we integrated those with a custom translation. And the other thing that we have customized is how we run the Python processes. The default in Beam is Docker, which is really nice because you can build containers with all dependencies that you like to use. They're easy to install, set up, and deploy. Unfortunately, we don't use Docker currently here, and also we have a different way of deploying Python code. It's laid out on the host machines already through the provisioning, so we can run processes directly. We customize that to better fit our needs. If anyone is interested in how these things look like, it's in the Lyft fork, which is public. One question that keeps on coming up is what's the performance of this, right? With FN API, all this chatter between SDK worker and runner, how fast or slow can that be? Well, first of all, we are talking about running Python code, so that's the first. I mean, we shouldn't expect like stellar throughputs, just like we are in the range of what we can do with Python. But nevertheless, it's good to understand a little bit what the overhead is. So I put together this little example, which is like running an empty bus, right? There are a few Python operations or transforms in there, but they don't do anything. I just wanted to see how many of these transforms can be executed, and to measure the overhead. What would happen when you write an actual pipeline, then you will have logic in those transforms, and the picture will actually shift. It will be your user code will be the large percentage of where the resources are spent, and the overhead will be very small. And the team at Google, before they implemented these protocols and API, they actually did some testing. I believe it was done with Java, and they figured out that the introduction of that additional process bears a 15% overhead compared to an execution with within a single process. So it's not too bad. Maybe the number is a little bit optimistic, but let's look at what we get here. So you see on the top, when the Flink pipeline on the top has operations in it. After it got translated, you have these the sequence of Python transforms fused together. It's called a fused operator that actually chains these things together, not done by Flink, but by Beam. So if you add any more operations in here, it will appear as one operator to Flink, not as multiple. That is important because instead of 5 interactions, you will have 1. The second part is bundling. As I said, bundles are groups of records that need to be processed. By putting many records into one bundle, we will again limit the chatter between the runner and the SDK worker, and that gives a great boost for performance. The third thing is that we need to parallelize the SDK workers because of the global interpreter lock of Python. Flink provides pipeline processing. It has parallelism all in one task manager, but with Python we need multiple processes to keep up with that parallelism. So we run multiple SDK workers on one box. And finally, for Python itself, there are several optimizations that we don't use currently. We still run this with vanilla Python. We could use Cython. We can also use the protobuf C++ bindings, which will greatly speed up the gRPC. So what we got here is a pretty good CPU utilization that you can see. And I was able to get it also closer to the 100%, but it's using the resources on the machines. Machine has 16 cores and 32 gigabyte. There are 16 SDK workers running on that box. And the bundle size in Flink is 1,000 records or 1 second, whichever comes first for one bundle. And with that, we get a throughput of 17,000 transforms per second per worker. So like 250K per machine, which is not bad. And it's actually far above what you will get with a real Python application. So we are talking more like single-digit thousand records. And before the presentation, I talked to someone about that, what some of our applications can do, pipeline that we have today with KCL workers, and it's even less than that. It's less than 1,000 per machine. So you can see this overhead is not too bad, at least in the case of Python. You can drive this, and this is before detailed performance tuning has been done in Beam. We have done a bit. We have removed some bottlenecks like caching of the functions in the Python worker and this bundling in the Flink Runner. And from a performance perspective, it's not limiting. It's your Python user code that will bound what you can do. What is next? So the recap is we can now do pipelines written in non-JVM languages on JVM runners. There's full isolation of user code. How we run the user code is configurable, i.e. Docker or direct process, or even embedded if the runner and the SDK language is the same. And we can, in the future, mix languages within the same pipeline, which we would like to use to just take the Java connectors that were already written and use them in the Python pipeline. That's the most obvious use case, and that's also what most folks are waiting for. The feature support matrix, you can see that the Flink Runner is pretty complete. The only thing that's missing is SDF, Splittable Do-Fun, which is the framework that will enable connectors in the future. And not just connectors, but connectors is an important application for it. That is not supported yet. In the roadmap, it's minimum viable product for Flink Runner is in place. The one thing that I mentioned already, SDF is missing to make it feature complete. There will be more focus on performance, and then the last big thing that's missing is a true cross-language pipeline support. So coming soon is that existing Java IOs, we have identified a path to make all of those enabled for Python without waiting for the full SDF support. There will be a wrapper that allows to run Java, all the Java IOs in a Python pipeline with a special case translation in the Flink Runner. Python 3 is a big deal for many folks. That is probably also something that they would wait for before they adopt it, and that should land soon as well. That has been in the works for a while and looks like it's going to wrap up soon. Then some better user documentation would be nice, and of course more portable runners. So if you want to learn more or get involved, here are a few links. There is also the link to this presentation if you want to check it out later.